Did you ever wonder where the asteroid that wiped out the dinosaurs came from? Hey there, tech enthusiasts! Welcome to Not So Techie, where we break down complex science and tech into bite-sized, easy-to-digest pieces. Today, we're diving into a cosmic mystery that has puzzled scientists for decades: the origin of the dino-killing asteroid. Recent research has traced this infamous space rock back to its birthplace, and it turns out it came from beyond Jupiter. Stick around to find out how this discovery changes our understanding of Earth's history and what it means for us today. Let's start with one of the most significant events in Earth's history, the Chicxulub impactor. This asteroid struck Earth about 66 million years ago, triggering the mass extinction event that wiped out the dinosaurs. But where did this catastrophic visitor come from, and why did it have such a devastating effect? Recent studies have traced its origins beyond Jupiter, offering new insights into this ancient cosmic event and opening up some intriguing questions about the nature of our solar system. The Chicxulub impact was a pivotal moment not just for the dinosaurs but for all life on Earth. It didn't just end the age of dinosaurs, it also created an environment where mammals, and eventually humans, could thrive. Understanding this event gives us a deeper comprehension of how life on Earth has evolved, adapted, and sometimes survived through catastrophic changes. It also makes us consider how delicate the balance of life really is, and how a single event can redirect the entire course of history. Recent research has identified the Chicxulub impactor as a carbonaceous chondrite, a rare type of meteorite that formed beyond Jupiter's orbit. These meteorites are fascinating because they are rich in organic compounds and water, the essential ingredients for life. This discovery raises tantalizing questions. Could these space rocks have delivered the very building blocks of life to Earth? And if so, how did a rock from so far away in our solar system end up on a collision course with our planet? The rarity of carbonaceous chondrites underscores Earth's cosmic bad luck. These meteorites make up only a small fraction of impactors today, yet one managed to hit Earth at just the right, or wrong, time to cause massive destruction. It's like drawing the shortest straw in the universe's lottery, but with consequences that reshaped the entire planet. Before this new research, scientists had already found clues pointing towards a carbonaceous chondrite origin. For instance, during a 2016 drilling campaign into the Chicxulub crater near Mexico's Yucatan Peninsula, researchers found a small fragment of carbonaceous chondrite. This was like finding a piece of the puzzle, but it wasn't the whole picture. Further supporting evidence came from elevated levels of iridium and chromium found in geological layers worldwide, marking the debris from the impact. Recently, scientists measured trace amounts of ruthenium metal in these layers, finding isotope mixtures that match those in carbonaceous chondrites. This ruthenium isotope analysis is like a cosmic fingerprint, making us more confident than ever about identifying the Chicxulub impactor as a carbonaceous chondrite. It's a powerful reminder of how every small piece of evidence can bring us closer to solving the mysteries of our past. One alternative theory suggested that the Chicxulub impactor might have been a comet rather than an asteroid. Comets, often called dirty snowballs, are composed mostly of ice and dust, making them quite different from rocky asteroids like carbonaceous chondrites. The idea of a comet being responsible for such a massive event was compelling because comets come from the outer edges of the solar system, traveling on long, elliptical orbits that bring them close to the Sun. However, recent findings challenge this comet hypothesis significantly. The isotopic evidence strongly supports an asteroid origin specifically, pointing towards a carbonaceous chondrite rather than an icy comet. This revelation is crucial because it shifts our understanding of how certain objects in our solar system behave and the risks they might pose to Earth. It also suggests that there's more to learn about the asteroid belt between Mars and Jupiter, a region that might hold more surprises. Another intriguing idea is that multiple impacts may have contributed to the mass extinction event 66 million years ago. Some scientists propose that other potential impact sites could indicate multiple collisions around that time. Imagine a period where Earth was bombarded by several large objects, each adding to the devastation. While it's an interesting theory, current evidence still points to Chicxulub as being primarily responsible for ending the age of dinosaurs. However, exploring other potential impacts can provide additional context about what happened during this tumultuous period in Earth's history. It makes us wonder, was this a single, tragic event, or part of a larger, cosmic chain reaction? Now let's talk about something even more mind-blowing, the panspermia hypothesis. This idea suggests that life on Earth might have originated from microorganisms or organic molecules delivered by space rocks like carbonaceous chondrites. It's a concept that challenges the idea that life began in a warm little pond on Earth, proposing instead that the seeds of life might have come from the stars. Carbonaceous chondrites are rich in organic compounds essential for life, such as amino acids, which makes them prime candidates for delivering these building blocks to early Earth through impacts like Chicxulubs. If this is true, then the very event that caused so much destruction might also have sown the seeds for new life millions of years before. Of course, there are other theories too. Some scientists believe deep-sea hydrothermal vents or volcanic activity could have provided the necessary conditions and ingredients needed to kickstart life here on our planet without any extraterrestrial help. These vents, found on the ocean floor, spew out hot, mineral-rich water, creating environments where life could potentially thrive. These alternative theories serve as counterpoints against panspermia, suggesting that life's building blocks might have formed right here under the extreme conditions present during the early stages of Earth's development. It's a fascinating debate, and each new discovery adds another layer to our understanding. To validate these theories further, future missions aimed at collecting samples directly from comets or asteroids similar to the Chicxulub impactor will be crucially important. Current missions like OSIRIS-RX are already contributing significantly towards enhancing our understanding by bringing back samples and helping us analyze their composition better than ever before. One might wonder, how does knowing the origin of the dino-killing asteroid help us today? In a nutshell, understanding the past influences how we explore the future. Knowing the composition and origin of the Chicxulub impactor helps us predict potential threats from similar space bodies in the future. Earth's cosmic history tells us that such catastrophic impacts, although rare, are indeed possible. This knowledge empowers us to prepare and potentially prevent future catastrophes, safeguarding our survival. This research also significantly influences planning for future space missions. Knowing the asteroid was a carbonaceous chondrite from beyond Jupiter allows scientists to target similar bodies for exploration. By understanding the composition of these ancient objects, we can better predict how they might behave if they come close to Earth. Exploring where the asteroid originated and its composition also supports astrobiology research. The panspermia hypothesis gains further traction with these findings, helping us better understand whether life might exist or existed elsewhere in our solar system or even beyond. Finally, with the goal of future asteroid and comet missions comes the challenge to improve space exploration technology. Tackling these challenges pushes the boundaries of technological and scientific advancements in robotics, artificial intelligence, and space exploration. Each mission not only teaches us more about our cosmic neighborhood but also advances the technology we use in countless other fields, from medicine to environmental science. And with that, we reach the end of our cosmic journey today. We've explored the origin of the Chicxulub impactor, learned about carbonaceous chondrites, and delved into theories about the origin of life. Each discovery, each asteroid, and each mission to the stars has the potential to revolutionize our understanding of our place in the cosmos. So, as we continue to look skyward and unravel these vast mysteries, always remember that our home, Earth, is just a small part of an even larger and more exciting cosmic picture. In science, the journey never really ends. It just brings us closer to the next fascinating question. That's it for today's episode of Not So Techie. Stay curious, stay excited, and keep exploring the boundaries of your knowledge. Make sure to subscribe, hit that like button, and ring the notification bell so you never miss an episode. Let's reconnect in the next one where we unravel yet another amazing piece of science or tech. Until then, stay safe and keep gazing at the stars. Thanks for joining us on this fascinating journey through space and time. We'll catch you on the next one.